Hello, I'm Umnik, and today I'm doing something very unusual. The description for the channel states that, among other stuff, that this channel is supposed to be mostly about competitive programming stuff, and as far as I'm aware, every video is more or less about competitive programming. Okay, there is like an interview video, but most of the questions are also about competitive programming. So, yeah, also about competitive programming. And this one is not. And I guess it kind of reflects the fact that for many years my life was mostly about competitive programming, and I think that in the last year I spent less time on competitive programming than on doing what is known as pencil puzzles or logic puzzles, stuff like that. And yeah, I just want to show them to maybe new audience. I don't know. Frankly, I just want to solve puzzles, and it would be nice if people watched me solving puzzles, but genuinely, I'm okay with nobody watching this video, and I will just solve some puzzles. And I will try to explain the logic. I try to solve everything logically, ideally, like without trial and error. And those puzzles are supposed to be like not very hard, so hopefully I will be able to solve most of them without big brute forces, trial and error, and like what it is called, I guess, in puzzle community, like bifurcations, when you just don't know what to do next and just try all options. So the puzzles I will be going through are coming from Genuinely Approachable Pencil Puzzles series, which is on Crack the Cryptic Discord server, which is, I guess, the biggest Sudoku and pencil puzzles community. Cracking the Cryptic is a YouTube channel where they solve mostly Sudokus, but sometimes also those kind of pencil puzzles. So probably if you want to watch this kind of video, you should probably do it there, not here. But yeah, I guess this is the part where I should like explain why should you watch me solving puzzles. You probably shouldn't. Frankly, I don't really understand why would people watch me solve like competitive programming problems, but there it kind of makes some sense, right? I'm one of the greatest, or at least I was one of the greatest competitive programmers in the world, and like a CPC champion and stuff like that. So it kind of makes sense to like try and learn from me there. Here it is not the case. I'm not great at solving them. I'm like okay, I think. Maybe like in top 1000 in the world, which is not great considering that I'm not sure that 1000 people do this thing competitively. So I have some experience, but I'm not good. I don't know. Yeah, I don't know why anyone would watch it. Although, like, I think it is more visually engaging than competitive programming, because something will actually happen on the screen, and it's like not me writing code, and you can follow it and the rules are like not super simple, but should be able to like be graspable in reasonable time. So it is probably easier to follow what I'm doing, even if you don't have much experience in it. So with that amazing introduction, we'll just jump right into it. So the series is called Genuinely Approachable Pencil Puzzles. I will put the links in the description to the Discord, and like where you can find them. The puzzles are solved in online interfaces. We will probably see puzzling and maybe penpa for some genres that are not supported on puzzling. There is also a similar series for Sudoku, genuinely approachable Sudokus. Both series post puzzles every day. This is a Discord, so this is today's puzzle. This Sudokus, I'm assuming. There are like different subgenres of Sudokus, or like variants. I'm not really into Sudokus, but so I don't do that. But I'm into pencil puzzles. I already did this puzzle. And the series continues to this day. They started, I think, like in late October of 2020. You can see that they have like 40 monthly digests. So it's in 41st month going strong. I will start almost from the beginning. Actually, I will start with the fourth series. I opened the third because in the fourth there is no like title list like this for some reason. Why I'm not doing the third? Because they did not put links to the examples. So there is a link to the puzzle after each puzzle, but starting from the fourth month they're putting like smaller examples and links to the examples. So the workflow will be like for every puzzle, I will read through the rules, then go to the example puzzle and solve the example puzzle, trying to like understand and highlight some important features of the rule set, and then jump into the main puzzle and try to solve that, also explaining what I'm doing and probably highlighting some features of the genre. I guess we can close this one. But the puzzles are probably great. I haven't solved these ones. I did solve the first volume yesterday. Went through the whole month. So I'm closing this, and we will start with February 2022. It should be okay. So I guess they messed up the year in the previous one. So yes, so I think it started in late October of 2021. This series is supposed to be like with genuinely approachable puzzles, so like kind of introductory, but on the other hand, I think they are like not that hard, but they also, I guess, have a goal of highlighting a lot of different genres. And even though I'm doing a lot of puzzles for the last year and before that also. There are genres that I'm encountering for the first time in this series that is supposed to be for the newer solvers. It is great, but it also means that you have to spend a lot of time like going through the rules and understanding each genre. I think it is great for like highlighting the pencil puzzles as a whole, because we will go through many different genres. But just like something to keep in mind that if you will want to like try to solve them on your own, and like I highly encourage it. I think it's a great hobby, and as I said, I'll put links in the description. So if you want, you can like try to solve the puzzles on your own and then watch me do it, or don't watch me do it. Just solve the puzzles on your own. That's also great. Okay, let's start solving puzzles. I will stop talking nonsense. For every day, right? So the date, then the genre name, and this is the name or like handle of the author of this particular puzzle. There are several people who contributed to the series. They changed slightly throughout the years, but yeah, there are like 10 to maybe 15, 20 people who contributed to the series, all great puzzle setters. So this is a castle wall puzzle by Tyrgannus. I'm not sure how to pronounce handles. Tyrgannus. And in every so they are like starting as Discord posts, and in every post there is some lore. I don't know why. If you're into that kind of thing, there is some lore. Okay, let's look at the rules. I will make it a bit smaller so that with the rules you can look at the examples also. But we will go through the example later. And Castle Wall is one of the genres I did know before. So rules. Draw a non-intersecting loop through the centers of some cells. The loop may not enter outline cells or cells containing clues. Clues are like these numbers and arrows. White cells with outlines must lie inside the loop, while black cells with outlines must lie outside the loop. Gray cells may either be inside or outside the loop. A number represents the sum of lengths of loop segments in the indicated direction. For clarification, loop segments are counted by how many times the loop crosses a cell border in that direction, and does not need to be continuous loop segments to satisfy the number clue. So, like for example, here we have like two segments in this rightmost column, segment of length 1 because it intersects one border, and the segment of length 2, so their sum of their lengths is 3, and like that, what that clue told us. And we can see that this white square is inside the area surrounded by the loop, and this black one is outside. And the gray ones can be either inside or outside. We don't have to use all the white cells, and the loop cannot intersect itself. Okay, let's look at the example puzzle. I mean, we have already seen its solution, but solving it on your own will give you some insights of like how the puzzle works, how the genre works. Also, like every good, well-constructed puzzle will have exactly one solution, and technically you can use it to solve the puzzle faster. That is a concept called like uniqueness. Sometimes you can say like if you draw some part of the solution in some way and then like continue to be with the full solution, maybe you can change it always so that it stays the valid solution, so it cannot be like that. I will not use such ideas. I'm actually not using them when I'm solving puzzles on my own, but people who are better in this competitively and solve faster, they do use uniqueness. Okay, let's look at the puzzle. So we have several types of constraints in this puzzle. One, like the main that like we are drawing one loop without self-intersections. The second type of constraints like are given by clues, these numbers and directions. And the third type of constraint are the colors of like black and white cells. So let's go through them in order. So the first type just kind of gives us like the general idea of what we should be doing. We will be able to use it like specifically a bit later. So let's start with like constraints of the second and third type that are like more specific and like they have locality. So for example, this one clue points at these two cells, and there can be only one segment here. There's just one border that we can cross, and we must cross exactly one border, so it must be there. We cannot visit this cell because loop just cannot go through there. And if we look at this two clue, there are two borders, we must cross them. We can also like continue this the loop further. But let's also look at the constraints of the third type, the black and white. So actually we could get like this part of the loop by the fact that this clue is white. It is white, so it must be inside the loop. We know that like outside the field is obviously outside the loop. So this white cell must be separated from the outside. So we must draw this part. And conversely, for this black cell, it must not be separated from the outside. Or like there could be line segments, but there must be even number of them. And like the parity is very often used in many puzzles, especially in the loop puzzles, because like for example for in and out constraints, if you start from the outside and like follow some path on the plane, if you intersect the loop odd number of times, you will end up inside. If you intersect the loop even number of times, you will end up outside. So since the cell must be outside, the number of intersections, for example, like this segment like this, must be even, but it cannot be 2 or more, so it must be 0, so we cannot visit all those cells. I'm drawing crosses to indicate that those like borders between two cells are not part of the loop. Technically, you don't need to draw like negative information for the solution, but it is useful for solving. Okay, so the loop cannot go there. There must be a segment here of length 1, so it's either like this or like this. And let's look at it like in general. I have two borders and they must intersect one of them. Two borders next to each other. So I must visit this cell, but also I cannot go through like this in this cell. So actually I must have a turn in this cell. And since I cannot go right from it, I will have to go left. So this segment is surely in the solution. Now we can also go back to the fact that we have to draw exactly one loop. And this implies some connectivity constraints. So all the segments that we are drawing must be connected to each other. That's not all the information we can get from the fact that we're drawing one loop, but it is true that everything must be connected. And we can see that we have this upper left part of the puzzle and, I guess left and right parts of the puzzle. They must be connected. So we don't have a lot of ways to do that. So we must go either here or here. Actually, we must do both. Because, again, parity, if we look at some area of the picture, for example, this left half of the picture, the loop must cross it even number of times, because every time we enter the area, we must then exit it. And so the number of times we cross the boundary of the area is even. Or you can say that if we start outside here and go down, we will end up outside below the grid. So we must have crossed the line even number of times. So we have to have both of those. Okay, now we can see that we cannot enter this cell because we would have a fork here. And to visit a cell, we must have two segments coming into it. So if there is only one direction left, then it's also not used because we're just not using this cell. Now we can use this one clue because we know that this segment is not used, so this must be used. And then just finish drawing the right part. And on the left, each one of those segments would be fine, but we have these two clues that we didn't use yet. We already have two borders intersected, so we will not use this one and go up from here. Okay. So now for the main puzzle. Starting from looking at black and white colors and the borders. Also another thing, when we have black and white close together, there must be a border between them, or rather there must be odd number of borders between them. And if we would have two cells of the same color, then there must be even number of borders. But here we can say that this border must be drawn, this border must be drawn. We have a lot of zeros. Zeros are nice because we just know that we don't use any of the borders here. Now we can see that we cannot enter this cell. We can also not enter this cell because it has only one entrance left. Now, if we use this cell, we must go like this, and this will close the loop. But we have another part of the loop here, so that cannot happen. And to exit, we must continue the loop like this, and then like this, because if we go up, again, we will just close the loop. This 5 looks like a lot. 1, 2, 3, 4, 5. Yeah, we must use all of them. White and black here, so have to separate them. cannot enter this cell because there is only one entrance left. Now let's look at this column. We have a clue of 3. We already have one segment here. There is one more segment here and 2 here. But we can see that those 2 we must either use both or not use both. So if we do not use both of them, we will only have at most 2 segments in this column, so we have to use those 2, and now this one must be left unused so that we have exactly 3 crossings. Now another very important thing for the loop genres, and well, I kind of already talked about it, but let's see this small 2x2 square. Like in puzzling I cannot draw on the borders, but yeah, this 2x2 square. It is a small area that again I have to enter and exit even number of times, and we can count that I have already entered it 1, 2, 3 times, so it must be even, so like at least 4, and there is one more entrance that can happen here, and so it must happen. Otherwise we would have odd number of loop ends here, which is not possible. Now we can see that this lower part is like almost a closed loop, so we have to continue both here. We have a 2 clue here that is already satisfied, so it cannot go higher, it cannot go through this point because it will close the loop. So that goes to the left. And what's next? If I go up from here, I will arrive at the dead point, so just go right from here, or you could understand it from that black clue here. Again, it cannot go up because that's a dead end. We are almost finished, like there is a small finishing area here. I cannot close the loop yet because there is, for example, this one clue that must be satisfied. Actually, it can only be satisfied here, so we can draw it like this. Yeah, we cannot cross to the path that is already drawn, so we will not visit any of those cells. And also there is this 4 clue. We have 1, 2 segments already and 1, 2, 3 options more, but again those 2 will either be both used or both unused. This is not a valid option, and if I don't use them, then it will be only 3, so I have to use them actually, and that should finish the puzzle. I will not use this one. We are done. So that was the castle wall puzzle from Tyrgannus. We can move to the next puzzle from Freddie Hand. Actually met Freddie on Sunday in UK Puzzle Championship. He won the championship, obviously, and I was like straight in the middle of the table. Okay, there is some story again. The puzzle genre is FiveCells. This one I also have seen before. The rules: divide the grid into regions of 5 orthogonally connected cells, pentaminoes. So like to see how it looks like, so there is our puzzle, and it is divided into the regions of 5 cells. Clued cells must have the indicated number of region borders or grid borders surrounding them. For clarification, P pentaminoes cannot have internal borders. You may have some questions. What's a P pentamino? P pentamino is like this, and there are like 12 pentominoes up to rotation and symmetry, and all of them have associated letters for the ease of use in the puzzle community. This is W, this is X, this is I, this is Y. I guess this one is like the most stretch one. Doesn't really look like an I. I mean, you need to like so this is supposed to go down, but still it still doesn't really look like a Y, but okay. So the clues that are given say the number of borders near that cell, so like how many of the segments surrounding the cell are used, including the borders of the whole field. So this 3 means that 1, 2, 3, including the border of the field, are used, and this one is not a border. And there are some hints for us. Notes for solving. You can draw auxiliary connecting lines by dragging between the centers of the cells. While these do not have to be drawn for the checker to trigger, they are very helpful for solving. That is true, and they're talking about like this thin lines connecting cells that are inside one component, so that like we mark that those cells are inside one component. The FiveCells secret: a clue of size n is adjacent to exactly 4 minus n cells within its region. Yeah, that just reminds us that every square cell has exactly 4 sides, and so like if n of them are borders, then 4 minus n are not borders and must be like neighbors inside the connected component. Let's look at the example. We can start with Z0 because like all of those must be neighbors, and we already have 5 cells, so there can't be any more here. Those ones on the border are also nice because they already have one border, so all others must not be borders. Now we can look at cells like here and here. If they're like for every cell and every component, either this cell is inside that component or not. So if it is not inside this component with 1, then it must be separated from them, but that would mean that this component is not of size 5. So it must actually be included here. And the same is true for this cell. This 2 is already inside a component of size 5. We're doing great. These 2 already have 2 borders, so those must be neighbors in the component. We can also look at cells near the borders we have drawn. Like the cell already have 3 borders, so the first one must be a neighbor, because like we must continue this component until it has size 5. And now we can look at what is the most of the puzzle usually about. Is the fact that like we have 2 components here already, one of size 2 and one of size 3. They technically can be one component, so we don't know that those are 2 different components, but actually they cannot be in one component. Why is that? Well, because those 2 and 3 are already 5 cells and they're not connected. So if we add more cells to that like supposed component that we want to build to make it connected, it will have more than 5 cells, so that cannot happen. So those 2 are actually different. And that means that this component, we must make it of size 5, right? And it must evade this component. So for example, if we continue this component down, then this one will be cut from the outside world and can only have size at most 3, so that cannot happen. And actually, this component must continue here. I was showing it like this, but I don't know if this cell is actually taken by it, but like I can imagine like what is the most it can take without going to the right. I'm like 1, 2, 3. It cannot go here because we know that those are different components. So this is 3, and then it has to take 4 and 5. Like, there are no other ways to increase this component. Now we have reached this 3 clue, and 3 clues are kind of like dead ends of the components because they have to have 3 borders, so they only have 1 neighbor. So this is not a border, so the other 3 must be borders. And actually we have to take this 5th cell to finish this component. And I guess we can do the similar logic with this, like 2 and 3. Again, they cannot be in the same component because that would be like 5 plus something else to make it connected. So they go down, and they have like 4 here, so they must go down again. And now this is 5, and we are done. And now for the main puzzle. Again, start with zeros. Zeros just give us those x pentominoes. Ones on the border are very nice. And we have this 3 near 1 that must be a dead end. Another usual thing is like those 2 3s next to each other, they cannot be connected. And it's not even about the fact that they're in the corner. If they're connected, then both of them must be dead ends, but that means that we have to draw like all the other 6 borders, and we don't get to FiveCells. That's the name of the puzzle. So we must go up from this 3, and if we go up, this is a dead end, but we have not finished the component yet, so we must go to the right to increase this component. We know that we cannot take this 3, so it must go here. From this 2, we cannot go to this 3 because this would be the end of this component. So we will go up, and since it was a 2, it must have 2 borders. So actually it's not taking this 3. Those 2 components are different, so we have a border between them. If we take a 3 here, that will be just the end. So we are actually not taking it. Like before I said that if we take it, we will still have to go to the right, because that 3 would be a dead end, and like we cannot continue from there, but we have to take more cells. But now we have shown that we actually cannot take it. So we draw a border, increase further here. Now we can connect this 3. Okay, for this component we will have to add 1 more cell, and we don't know where to do that yet. Okay, so let's look at some other places. These 2 already have 2 borders, so it's like this. Now this is a border, and yeah, the thing they said like that the P pentomino cannot have internal borders means that if we have drawn a border, it means that those 2 cells must be in 2 different components, so we cannot continue like this. So there is actually a border here, and we go further up. And again we have 4 cells, we need 5, so we will take either this one or this one, but we don't know which one yet. Okay, we have kind of cul-de-sac here, so we have to go from outside, and we cannot connect those 2 components because they will be too big. So this finishes this U tetromino. We cannot go down here because this must be a border between two different components. We cannot have this connection because this one doesn't have enough neighbors, but we have already finished like the component, so size 5. Or we could also say that this cell must escape, so now we have 5 cells here. And now this one has one border it needed, so all others must be neighbors. This cell must escape somewhere. Now we have this F pentomino, again one of the stretches in the letters. Now those parts must escape, and we have 5 here. This one must have the neighbors, and this 2 must have another neighbor here. So we have this P pentomino. Now this can go right, and now we can finally finish this pentomino here. This can go further right, and this must escape. This finishes at that pentomino. Now this 2 has 2 borders, so the other 2 must be neighbors. Here's another interesting deduction. We cannot add this 3 to this component, because if we add it, we must also add it like this, right? I mean, if it's in that component, then it will be neighbors with all the nearby cells that are in that component. But that 3 must only have one neighbor, so we cannot take it. Okay, now we have this component of size 3 that we must continue. It cannot go down, it cannot go up, because that would be too big component, so it must continue to the right and end here because it's 5 cells. Escape from this 3, escape from this 3. They cannot connect because that would be 6, so it continues here. Okay, now we can do a bit of counting. I guess it's not needed, but it's just a fun technique that I can show you. So we know like about all of these borders that are drawn, and we can see that there is like this space that can escape only in one way. We can count the number of cells in this zone, and it is like 1, 2, 3, 4, 5, 6, 7, 8, 9. What do we understand about 9? Like, what if we draw a border like this? Then this 9 must be fully covered by pentominoes, but that is impossible, right? So this must connect like this, and now it has like 10 cells, and now if we continue it further, then it's also bad. Because like if we look at this component on the border, like it is separated in the part that is higher and lower, and we know that the part that is higher must be of size 4, so that the remaining number of cells there is divisible by 5. So the part that is lower must be of size 1, so it must end here. And that should finish the puzzle pretty much. 3 and 4 we cannot connect, so it goes like this. Escape from there, and so that's 4 and 2. What is this? Yay! Puzzle number 3. I don't know how to pronounce it. Ayeheya. Well, it's the name is built from Hayawake, because it's Hayawake variant, and the name is built because like it's Hayawake where the regions must be symmetrical, so they made a palindrome like from this Heya part. Yeah, the the thing about this video and maybe further videos that I might do on the Genuinely Approachable Pencil Puzzles is that even though it is supposed to be like for new solvers, still they want to cover a lot of genres, and well, genres they tend to build on each other, right? They don't like come from nowhere, and there is also a thing like a genre variants that like try to add new constraints or like some new ideas to existing genres, or maybe like fuse two genres, stuff like that. And well, also I'm starting like not from the beginning of the series, so it's very likely that they had a Ayeheya puzzle before in the first 3 months. So like given a variant on a puzzle is not that crazy, but for us, like it looks like okay, it's a variant of a puzzle that we don't know. Well, I actually do know, but I mean, they will still explain the rules. So they will give the rules of this particular puzzle, but those rules, oh right, they're even split. Like yeah, so these are the rules of Ayeheya, and then they give additional rules for the variant. And so like for solving, it would probably help if you do something about Ayeheya. Well, tough luck. Okay, rules. So first, like Ayeheya rules. Shade some cells so that no two shaded cells are orthogonally adjacent and the remaining unshaded cells form one orthogonally connected area. Numbered regions must contain the indicated amount of shaded cells. A line of consecutive unshaded cells may not cross more than one bold border. There is kind of like a lot of things going on in those rules. Well, first of all, it's a shading puzzle, so like for every cell we must either make it black or not, and usually like the cells that are not made black are made green or maybe like put dots in them. Puzzling actually doesn't follow consistent strategy on that. So like for Ayeheya, for example, they color them in green, but for Tapa, for example, they put dots inside of cells, and I don't like that. I want green. I want green color. Or just color, so that cells that I know are unshaded are visually distinct from those that I haven't decided yet. Okay, so whatever. We shade some cells. We cannot shade two cells that are connected, that like have common side, but we can shade two cells that have a common corner. And the remaining unshaded cells, so the ones that are green here, form one orthogonally connected area. So they are connected by fork connectivity. Numbered regions must contain the indicated amount of shaded cells. So we have some regions indicated, and for some of the regions, it is given that, like for example, this region must contain 2 shaded cells, and here they are. And this region must contain 4. But this region, for example, can contain any number of cells. So why it is given? Well, because there is another rule about regions. Actually, there will be another rule about regions for the variant, but like the vanilla Ayeheya rule about regions, it is like more about borders of the regions actually, and it says that we cannot have a segment of green cells, of an unshaded cells, that crosses more than one bold border. So for example, this cell is blackened, because if it was green, then we would have like this segment of length 5 that has two bold borders inside. That is not allowed. So those would be Hayek rules, and our puzzle is a variant. And the additional rule is that the shaded cells within a region must have rotational symmetry around the region's center. So like for every region, well, in this case, and for this case of the puzzle itself, all the regions are rectangles. It is technically not required, but it is considered for a classical Hayek that like regions should be rectangles. Because of the border rule, like it is not great when a region is like non-convex in a sense, so that you can leave it and then go back and you cross two borders. I mean, it's fine, and technically like you can draw bold borders inside the segment, the regions, like they. Unlike like what we saw in FiveCells, right? Like we cannot draw a border here, like inside the region. But technically, nobody stops, unless like it's definitely forbidden explicitly. And those like non-rectangular regions and internal borders are okay, and like you can build puzzles where like there is just one region and just everything is like filled with internal borders, but everything is one region. That's fine, but it's not like classical. Okay, the symmetry rule. Well, it's hard to see right now. I mean, you can see that every region is symmetrical. Like this one, the center of the symmetry is like the point of intersection of diagonals of this rectangle, and like if you rotate it 180 degrees, it stays the same. So yeah, it's rotationally symmetric. How to use it in the puzzle solving? Well, we know like which cells must be the same, so if we color one, we can color the other one. Okay, let's go through the example. I don't really like fake puzzles. I'm kind of bad at them, but we'll see. Okay, so the starting point for Hayek puzzles is usually like small regions with big numbers, because we need to pack those black cells. And actually, like since you cannot have two black cells together, it is like a reasonable idea to look at the like domino coverings of the regions. And for every domino like this, we can have at most one cell blackened, so there is at most one blackened here, so this must be blackened to have two. Now those are unblackened because we cannot have two neighbors. This must be blackened. Now we cannot blacken this one because this green must escape. We have connectivity on green cells, and well, this basically like how the puzzle flows. We have some constraints about like we must have some number of black cells, but then there are connectivity issues, so we must have green cells, and then we have less place to less space to place black cells in a region, so it continues. And also at some point we might use the border rule. Okay, let's use symmetry actually. Although like maybe this puzzle is like more or less solvable without symmetry rule, but let's use it to get a grasp of like how it looks like. Like in this region, for example, this must be also green because like those two cells must be the same, this two must be the same, this two must be the same. In this region, this must be green, so this must be black, because we must have one black in this region. Actually, we can use symmetry even smarter, and we can say, like, right away, without drawing anything, we can just say that, okay, in this region, this must be black. Why is that? Well, because all other cells are split into pairs. And the only way we can have exactly one black cell, or like odd number of black cells, if the middle one is black. Otherwise, we will always have even number of black cells. And so, like, since it's one, all others must be unblackened, which is super nice. And we can return all the information we got. Those must be green because of connectivity. Again, symmetry gives us those green. Okay. In this region, we cannot have two black, because we cannot have two black near each other, but it must be symmetrical, so they must be both unshaded. Now, in this column, we can use the border rule. If this is unshaded, then this will be bad. We have two borders inside one green segment, so this must be shaded, and then this must be shaded because of symmetry in this region. And for here, no, this must be unshaded, because if one of them is shaded, then the other is symmetrical, so it's also shaded. And like, if we have two cells that are on the border of the center of the region, they must be unshaded, because otherwise they're both shaded, and this is bad. And now we have 4 dominoes with 4 shaded cells, so we must shade one in every domino. So basically in each square there will be a diagonal, like this or like this, and for this left square it is fine either way, but for this square, if we draw a diagonal like this, we will block this cell, it is not connected, so it must go the other way around. And now by symmetry we can choose what is the right way here. It must be symmetrical, so it must be like this. Okay, the example was kind of small, but let's go to the big puzzle. Okay, we again have this 1/3 with 2. It must be like this. We have a border rule here, and we have symmetry. Don't forget about symmetry. Symmetry just gives us a lot of stuff. In this region, we could draw a diagonal like this, but then we have disconnect, so it must be unshaded actually. Those two cannot be shaded because they must be equal and they are touching, so they are shaded. Same here, so those two must be shaded. Don't forget about symmetry. Those are like the same idea. The center lies on the border between two cells, so they must be unshaded. And here also. Now here we have a border rule. If this is unshaded, then we have two borders. Symmetry. Again, border rule, symmetry, more symmetry, and the border rule here and here, and finish by symmetry. This green must escape, and by symmetry this also green, but also this green must escape. Right, what's next? Now border rule here. If this is green, and we have two borders. You cannot have shaded here, like for the same reason it was here, basically. This one will be blocked. So now we have border rule here. Border rule here. If this is green, then we have two borders, so it must be shaded. This might be shaded by symmetry. This green must escape. Border rule here. Border rule here. Now this one is a pretty cool border rule. This cell cannot be green, because if it is green, then this is also green by symmetry, and we have two borders, so they must be black. And we have the last border rule here. Yay. And as you see, like, this is a solved state, because like we only need to shade. So white, I kind of consider it green by default. So if you marked all shaded cells, it is good. Okay, so this is already an hour. An hour of talking is a lot, but okay, let's do one more. February 4th, Square Germ by Eric Fox. Divide the grid into square regions of orthogonally connected cells. A number indicates the side lengths of the square it's in. Region borders may not form any four-way intersections. So it's again like a region division puzzle, as was FiveCells. So now we are splitting into squares of different sizes, and the sizes are given by some of the clues. And there is like a weird, innocent looking rule that is actually like the meat of this puzzle. Region borders may not form any four-way intersections. So like for any internal point, we cannot have four segments coming in all four directions. Let's look at the example, how that works. So this one must be square. Cool. This too, like obviously it will be a square, like on the left border, so it must also contain this cell. So this will be one of the borders. Can it go lower? If it goes lower, then we will draw something like this, and this is what's forbidden. Those four-way intersections are not allowed, so it cannot go lower, so it must go higher. This 3 must go like this. This 3 must go like this. So it must be a 3 by 3 square in the corner. Because all of them must be in the same component. Okay. Now this cell cannot escape like higher or lower. It cannot be inside of a square of size more than 1. So it must be of size more than 1. And now like what is the usual deduction in this puzzle is that we have this point that is surrounded by, like, it has 3 borders coming into it, so it cannot have the 4th one, because that would be a 4-way intersection, which is forbidden. So those 2 cells must be in the same square, therefore those 4 cells must be in the same square, because like the side is at least 2 now, so it must go in at least 2 in different direction, but in this case it reaches the border, so it must be a 2 by 2 square, and here we just split into 1 by 1. And the same kind of situation here, those 2 must be in the same square, so this 2 by 2 must be in the same square, and it cannot increase further because it reached this border we already have, so it must be a 2 by 2 square. Now this 2 by 2 square cannot be split into 4 1 by 1s, because like this 4-way intersection or this one, so it must stay 2 by 2. This cell must stay as 1. Now here we cannot have a 4-way intersection and split the remaining part. Oh yeah, and you can see that it's in a different interface. So this is called PenPa Plus. The previous ones were on Puzzlink. Let's try the bigger puzzle. It might look quite easy, like, well, just fill with squares, but it is actually quite tricky genre. Okay, those 3s on the borders look interesting. The 3, like, it must go at least 1 to the right, because otherwise it will take this cell that is already used. But also it cannot go 2 to the right, because it will then take this cell that must be inside a square of size 2. So we cannot take it. And this 3 by 3 square must be like this. Here we don't have a 2, but still it must go 1 to the left. Right. This 3 must be at least like 3 away from the border. Now it cannot go 2 down, so it must go 1 up. And now, well, we don't know, maybe it takes this 3. This 2, on the other hand, we know that it must be like this. And kind of one of the usual situations, if it goes higher, then we will see that this square must be a 1 by 1 square, and we will have a 4-way intersection here, so it must go lower. We don't have a choice here. Now those 2 must be in the same square, and now they take this 2, so it must be a 2 by 2 square. If we wouldn't have this 2 here, it could have been bigger, but since we have this 2 inside this area now, it must be a 2 by 2 square, so we already finished with it. Finish this one. Again, we can't have a border here. Goes like this. Now if we increase this square further, it will connect with this one, but it goes further to the right, so that cannot happen, right? Like, if this is a connected component that is a square, it must also take this cell, which cannot happen. So it must stay 2 by 2. Now we understand that the lower border of the 3 is this line, so it must take this 3. But it still can go like to the right or to the left. I don't know yet, but we know that this is 1. And this also must be 1, because like higher it would have to take this cell. And now we cannot have this 4-way intersection, so this 3 by 3 actually has to go like this. Okay, now we can look at this cell, for example. if it is a 1 by 1, then it's bad. We have a 4 intersection here, so it must not be 1 by 1, but the only way it can be more than 1 by 1 is if it goes like this and becomes 2 by 2. Now these two are together, and so they go further, so they join this 3 group, and they have to be in 3 by 3 square. This is a 2 by 2, this is 1, these two together, this border. Now it can be bigger, but we know that this border must continue at least to here, so we'll have 1 by 1 square here. And actually we can have several 1 by 1 here, and those are all non-borders, so we have a 4 by 4 square here. Now we can see that these two cannot actually go further, it must stay 2 by 2. This is a 2 by 2. This is a 2 by 2. And we are done. Okay, that's enough for the first video. If anybody is still here, thanks for watching. And I mean, as I said, I just want to solve puzzles, and I will probably do one more and then one more, and well, we have like 40 months of those puzzles ready, so it's more than 1,000 puzzles. A lot of content to enjoy. Also, yeah, a couple more words about the series. Oh, Eugene, that's a good one. There are also some bonus puzzles each month. Usually they're like in one of the genres that was covered on one of the days, but probably like the setter tried to construct a puzzle and like they came up with this, but it was decided that it is too hard for the series, so bonus puzzles are usually a bit harder. But sometimes, like for example, this is a leads puzzle, and I don't think there was a leads puzzle in this month. Yeah, no leads. And also there are like target times for the puzzles except the bonus ones. So like for every puzzle, the setters decided that like if you are getting like under some time limit, you're getting the title of Speedy Sloth, and under some more lenient time limit, some quick crap. And also, like, yeah, they put it in every daily puzzle. The times are under spoilers, so like you don't get the ideas about the perceived difficulty, but also like it is not supposed to be competitive event, so like times are just to track your progress, but like if you're not doing them fast, that's also okay. And that is emphasized by the fact that even if you like don't finish fast enough, you still get an animal, and it is a bird, and unlike Speedy Sloth and Quick Crab, it is a different bird in every puzzle. So maybe it's better to get birds, right? Like, what's better, 100 sloths or 50 different birds? I think 50 different birds is more cool. But for this puzzle, yeah, I got a Speedy Sloth. Yay, I'm a Speedy Sloth. But it's not true for every puzzle. Here it's crap. And a couple of times I didn't get even a crap. So, as I said, I'm not good at them. I encourage everyone to try. It's super fun. And again, thanks for watching. Bye.